Hey guys, so this is my Physics 2211 Lab 4 submission for oscillation. So first I'm going to talk about the lab, go through the video, maybe look at the starter code, and then we can talk about how everything went down. Um, First, I'm going to talk about what the lab was specifically asking for. So first for this lab, we were given a video. This is the video. We can play through it real quick of a spring oscillating left and right. And then we had to put that video in Tracker and extract a CSV file from it and use this closed script starter code along with the CSV file to extract some key graphs and data from it. So first, I'm going to go through what the lab is talking about, follow all the rubric guidelines, and then we can actually talk about the data and the what-if questions. So first, this lab overview. This lab explores the motion of a spring mass system oscillating in two dimensions, both experimentally and computationally, to analyze and compare the observed versus the predicted behavior. Our key goals were to extract the position data using Tracker, model the system computationally in GlowScript, and evaluate the energy conservation oscillation periods. Here are some models and concepts that we use. So we use oscillatory models throughout the lab that we coded through GlowScript to simulate the motion of a mass spring system, swinging in two dimensions and analyze its energy transformations over time. So first, we can talk about Hooke's law. Hooke's law basically says that the scoring force of this force is proportional to its displacement from equilibrium, F equals negative kx, where k is a spring constant for the spring. We also talked about conservation of mechanical energy. So we have kinetic energy, which is 1/2 mv squared, and we also had potential energy, which can either be mgh or for a spring, it's 1/2 kx squared. And we talked about how this remains constant, but the kinetic and potential are constantly changing to balance each other out. We also talked about simple harmonic motion. Simple harmonic motion is the entire premise of this lab, so it's kind of important, and we're going to be talking about it kind of in the graphs. So our main result is that our computational model successfully simulated the two-dimensional oscillatory motion, and we replicated the trajectory and energy changes observed in the experimental data. Note the experimental data is a bit different from ideal data. We're going to talk about that in a second. Let's get into the what does it mean question. So first of all, I want to show you guys our graphs. So this is our position graph that we found. These are our energy graphs. We're going to have to get back to these for the what if questions though. So our what if question asks, from your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of the energy changes. So to answer that question, yes, the energy principle is satisfied in the model system. The plot shows that the total mechanical energy remains nearly constant throughout the motion with slight fluctuations. So if we go to the energy principle, we can show that the energy principle is showing the same sinusoidal trajectory as what it should, as what the model is showing. We can just see that the length of the graph, the length of the oscillation is slightly different, and this is because of some errors. Now we can talk about what if question 2. What if question 2 asks, using the data you obtain in Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation for the x, and second, by estimating the acquisition data for the y. So for this, we found the period of oscillation for x to be about 1.64, and for the period of y to be 1.53. The difference between these periods could result from several factors, including misalignment of the motion plane, leading to small out-of-plane moments that are not captured accurately by Tracker. Also note that we are selecting the frames. We are selecting our data points frame by frame in Tracker, so that could create some inaccuracy as well. I hope I answered all of your questions. I just want to note that some errors for the lab could be the fact that we don't have enough data points to create a cohesive graph of the oscillations. There's also some noise that we aren't accounting for that experimental data has. And as I talked about, Tracker's not perfect, Tracker's not ideal. That concludes my lab. Thank you guys.